All right, the next question here that we're going to take a look at is number 6. So this one is looking at asymptotes, both horizontal and vertical asymptotes of this function 5x minus 10 over 3x squared minus 3. Now, one thing to note is that we're going to have vertical asymptotes anywhere where the denominator is 0. And in particular, right, we would want to kind of keep in mind, like checking that there's nothing in the numerator that cancels out with the denominator, because that usually means there's a hole in the graph, not an asymptote. So if I factor the numerator, I'm going to get 5 times x minus 2. If I factor the denominator, well, I could say, well, first of all, I can take the 3 out. So this is x squared minus 1. Again, we get a difference of squares. We use that quite a bit. So 5 times x minus 2, 3 times x minus 1, x plus 1. So sure enough, nothing cancels out here factor-wise. So we can really just look at that denominator and say, okay, so it's going to be a problem if x minus 1 is 0. So x equals 1 is one of our asymptotes. And it's going to be a problem if x plus 1 equals 0. So x equals negative 1 is the other vertical asymptote. Asymptotes are lines, right? So these should not just be 1 and negative 1, because then we don't know if we're talking vertical, horizontal. We should be saying x equals 1, x equals negative 1. That's very clear that we're talking about two lines that are vertical. And we did have a lot of folks kind of switch these as far as vertical, horizontal. So the x values, right, a constant x value is vertical, a constant y value is horizontal. Okay, so how about the horizontal? How do we figure that out? Well, one common mistake was we set the numerator equal to 0. And the thing is, the numerator being 0 is not a problem, right? If a fraction, it has 0 in the numerator and some number in the denominator, that just means the function is equal to 0. That means we have an x-intercept. So that's not really what we're looking for. What we're looking for is essentially the limit. So we want to say, okay, what happens in the long run for something of this type? So 5x minus 10 over 3x squared minus 3. And because, again, we've done a couple of these before, so I'll kind of cut to the chase. Because the degree in the denominator is larger than the degree in the numerator, right? The bottom is going to grow faster than the top. That means this thing is going to 0. So it's not just going to 0, it's going to y equals 0. So that's going to be our horizontal asymptote. All right, for number 7, I chose a limit definition of the derivative. Now, we've done a limit definition of the derivative sort of piecewise, right? Because or piecemeal rather, because we did the difference quotient first and then we applied the limit. So we really did do the limit definition previously. But this one is explicitly calling this out. So if you used a rule, that is not what we were looking for. So we have g of x. We want to know g of x plus h. Now, here's where we got to be careful. I replace x with x plus h, but we got to do that with parentheses, right? This is going to make a difference. If I don't have parentheses here, everything goes out the window. All right, so if I want g prime of x, first of all, I should probably label that. Secondly, I should probably say how I find it. I find the limit of g of x plus h minus g of x all over h, right? If we didn't remember that, all we had to do was hop back up to this problem and go, hey, wait a minute, I feel like the definition was in here somewhere and I gave us everything but the limit. So the limit is h goes to 0 of our difference quotient there. And then we just say, okay, cool. The limit sticks around. Again, I think we had a lot of folks drop the limit off and then later on maybe pick it up or not have it at all or put it in just at the end. You know, we got to be really careful about this. If you're going to do that, you have to label exactly what you're doing and kind of point out why the limit isn't there, or not include equal signs and then just pull in a limit from somewhere. So, all right, we go g of x plus h minus g of x all over h. Now, these two things we want to have a common denominator in order to put them together. If we're going to do that, one thing we could do is say, hey, they already both have an 8. We don't have to bring more 8s into the equation here, right? So we can just say the first fraction is missing a factor of x. So I'm going to bring an x into the numerator and into the denominator. The second term is missing a factor of x plus h. So I'm going to bring a factor of x plus h into the numerator and into the denominator. If you chose to bring a factor of 8 into both places as well, that's fine. It's a little redundant because they both already have 8. We don't need to bring an 8 in, but if you did that, that's okay. It would have come out in the wash later. So now we can combine our fractions, right? They have a common denominator. So 3x minus 3 times x plus h over 8x times x plus h. That is your numerator, and then over that is h. Okay. At this stage, it's really tempting to cancel the x plus h, but x plus h is not a factor of the numerator here. So we have to keep going with our algebra. We got to work through some of the pieces. So we're going to say limit h goes to 0. You can work through these and kind of cancel them, and I might take, well, actually, let me just be incredibly clear, because that's really what I'm expecting of everybody, is distribute that -3. We know what's going to happen is those cancel, and I'll show that in just a moment. Okay, so we have this divided by h. So the 3x and the -3x are going to cancel. That is a good thing, and eventually the h will cancel, but you know, if we have this all happening at once, it becomes this like crazy cancel fest, and it's really hard to tell what's going on. If you just cross out a bunch of stuff, it's like, great, that made sense in your mind, but it's got to make sense to the person reading the problem, and so you have to keep that in mind. You know, treat it like you're handing it to somebody else in class. So the other thing I would say is h, right, divided by h, you can think about it like h divided by 1. The reason I say that, fraction divided by a fraction, you can multiply by the reciprocal. So that's not a crazy step to take, right? We really only simplified the numerator here and then thought about division like multiplication. This allows us to cancel h. And so here, we're going to get the limit as h goes to 0, right? I've been carrying this limit through. It takes me 1 second to write. So I've been carrying it through because I haven't used it yet. In the numerator, I got -3. Denominator, I've got 8x, x plus h. Now I'm in a place where I can apply that limit, right? Up until that point, I had an h in the denominator. Everything would have gone awry. But now I can get rid of the limit and say, okay, I'm going to plug in 0 for h. And so what do we get? We end up getting -3 on top, 8x squared on the bottom. So that should have been our final answer, is that g prime of x is -3 over 8x squared. Because we had learned the rules for some derivatives anyway, up until this point, you could double check, right? Like in your head, we could have said, well, okay, g of x is 3 over 8. And this x is in the bottom. I could have thought about like x to the negative first, right? Our rules would tell us that I could bring the negative down and subtract 1 from the power. If you gave me this answer, I knew you just used the rule, right? It would have skipped everything here. But again, we go, hey, I know this rule. I can double check in my head, right? And the way to rewrite this, of course, is that x to the -2, I can put that in the bottom of the fraction. Oh yeah, there we go. -3 over 8x squared, bam. But we should be showing this through if we say the definition, the limit definition of the derivative. Okay, I talked through 8a. I mentioned that one in class. I'll take a look at 8b. There are a couple of ways to do 8b. One of them, kind of the most straightforward one, is to multiply by the conjugate. So x squared plus 3 plus x. And I think a lot of folks miss the plus x. The other part of this is if you're going to multiply on the top by something, you got to multiply on the bottom. You can't change this function fundamentally. So we have to be really, really careful in how we do that. Okay, so then we say, great, if I'm multiplying this in the top, again, we have basically the factored version of a difference of squares. So we should look at something along the lines of a squared minus b squared. Well, a is this square root. If I square that, the square root goes away. So we're going to get the meat on the inside there. We're going to get the x squared plus 3. And then I have negative x, positive x. So that's a minus x squared. Oh, that's a thing of beauty. That'll turn out well. And then in the denominator, all I have is the square root of x squared plus 3 plus x. Okay, we know we're going to simplify this a little bit, so the x squared terms cancel out in the top. So we get positive 3 upstairs now. And then we kind of leave the denominator alone. Now here's the thing. The top is a constant, right? This guy is just staying 3, constant. All right, the bottom, let's look at what happens. We have a plus sign. There's no ambiguity about what happens here because both of these terms go to infinity, right? The square root of x squared. Well, if I keep increasing x, I let it go to infinity, then this thing goes to infinity plus infinity. This thing is clearly going to, or going in the direction of infinity, right? So if I have a fraction where the top is a constant and the bottom keeps getting bigger, right? Bigger and bigger and bigger, where's this thing going? This thing is clearly going to 0. Okay, so our final answer should be 0. Here's the trouble. If we did not do something along these lines, and this is not the only way to solve this, but it is a way to solve this. If we did not go through this, unfortunately, what we would have gotten if we started back with our limit here, and we did the thing that personally always makes me cringe, of plugging in infinity and seeing what happens. Well, we would have gotten infinity squared plus 3, okay, minus infinity. First of all, I hate this. Infinity is not a quantity. It should not be a thing you plug in, but it is a thing that a lot of people do, especially, if you are more of an applied mathematician or somebody who's just using math but is not a pure mathematician, whatever, it doesn't matter. But the square root of infinity squared, right, the 3 doesn't even matter. This looks like infinity minus infinity. That number sometimes is 0. It just so happened we got 0. But there are a lot of times when that is something else. This is one of our indeterminate forms. Just like infinity over infinity. Just like 0 over 0. Right? We have all of these different indeterminate forms where we go, okay, I need to investigate a little bit more because infinity is not a quantity. So it turns out this one is 0, but we can't rely on that always being the case. All right, hopefully those were helpful. And again, kind of keep in mind, a lot of these are very, very, very similar to what we saw in the test review and problems we've done in class. So keep that in mind just as a study strategy moving forward for the next tests.